So in our last video we was talking about graph traversal algorithm. We explained our graph traversal algorithm and what they are used for. And the first graph traversal algorithm that we have talking about was DFS graph traversal algorithm, breadth first search. So if you didn't watch that video, I highly consider you go watch that. So in today's video we're going to talk about another graph traversal algorithm, DFS, depth first search. So DFS is another fundamental graph traversal algorithm. It is used to traverse a graph or tree data structure. It starts from a starting node and explores as far as that it can before backtracking. So basically, to implement a DFS algorithm, you just need to use a data structure that is called last in first out, a data structure like a stack or a DQ. Basically, a stack is basically like a stack of plates. Like if you have a stack of plates, you stack them one by one, and if you want to remove a plate, you're not going to start from removing from the bottom, otherwise the stack will fall. You need to start removing from the top, meaning the last thing that you put on the stack of plate, the last plate you put, that is basically what is a stack. So let's go to an example of a DFS traversal. Basically, a DFS algorithm begins to search at the root of the graph, like at the starting point, and then explore each vertices by following a single path until it reaches a endpoint. Then if you reach a endpoint, then the algorithm is gonna start backtracking to explore another path until it reaches the root. So basically, in other words, DFS just explores every single path that is possible in a graph. So this type of algorithm is very useful to, for example, exit into a maze. So you just take one path until you reach the end, and if it is the exit, you win. If not, you backtrack and try another path. So let's see an example here. Let's take this graph here. We have 1 2 3 4 5 6 nodes here that are connected. So basically, let's say we're gonna do a DFS traversal algorithm. So we're gonna start at a starting point. Let's say we're going to start at node. This is our start at node A, as you can see here. So let's continue. So since node A right here, we're gonna explore his neighbor, his vertices. So we got B and C that's gonna be added into our stack. So right now our stack will contain B and C. So since we have a stack, we're gonna remove the last element that was added. Let's say in this case we added B and then C, so C will be the last element added. So since C was the last element added, we're gonna treat C. So we're gonna take C and we're gonna add again his neighbor. Since we already processed A, so we don't need to add A. So we take C, we add his neighbor B, D, and E to our stack, and let's say again that E was the last element that was added. So as you can imagine, we're gonna treat E next. But as you can see, we didn't treat B yet. That is why using a stack is so useful. So we're gonna start here. We started from A, we added B and C into our stack. Since C was the last added, we're going to try C, and we added D and E. So right now E, we're gonna treat E here. We add his neighbor into our stack, and as you can see, F was the last added, so we're gonna treat F. And as you can see, in this traversal we explored this path. We did this. After that we did this. That is basically our first traversal. As you can see, we only took one path to go to F, but as you can see, there are a lot of paths that we could have took. So basically, after have finished treating node C, as you can see here, we're gonna backtrack, meaning we're going back to node B here, and we're gonna treat his neighbor. That would be C, D, and A. But as you can see, A and C was already been treated, so we don't need to treat it again. So we're gonna treat node D, and as you can see, because we already treated F. So basically that is DFS. Let's just open this animation and see it. If you go see our animation, we can see the DFS graph traversal algorithm. As you can see how the algorithm is traversing this graph, A and B, C, D, E, and F. This is basically an example of a DFS traversal algorithm. So let's go ahead and implement this DFS function. So I'm using a notebook here. So let's implement our library that we're going to use. So let's run this. Every library is installed for you. Everything should work fine. So first we're gonna have our graph representation. So let me just copy our graph here. As you can see, we're using a dictionary list to represent our graph. So this will be our graph. So let's do our DFS function. So let's just define a function called DFS. 2 parameter, our graph, and a starting point. So like I said, to implement DFS we need a stack. So let's just define a stack, and that will be just a list that we can use as a stack. So, and our starting point, then we're gonna have a list that will show us our traversal, our path, and we can continue. So while there is a element in our stack, so let's maybe just add these to just make sure that our traversal is displayed properly. So okay, so let's print what are the elements in our current stack. So start, let's print our stack. As you can see, okay, so we're gonna remove our last element into our stack. To do that, we're gonna use the pop function into a list to remove the top element, the last element added. So we're gonna print our current node that we are treating right now, current node. So let's print out current node, as you can see, and then for every edge in our graph current node, for every edge, if we need to check if this edge is not already been treated, so not in parent, so we're gonna add it, that edge into our, the edge is not already been treated, we need to add it into our stack. So let's just add it into our stack and then print the element added to stack. So edge, and then let's just add this into our path. So path that append parent edge C. Okay, so after that we just need to return our path. So I think that is here. This is basically a DFS algorithm. So let's just run it. So let's just try to call a function. So let's call our DFS function and a graph and a starting point, not a to see. Oh, let's just print it just to make sure. So let's just run it. Oh, there is, oh, sorry. Let's see. Okay. Okay, let's run it again. Okay, as you can see, there is basically what we had here in our example, and here A, B, C, D, E, F. As you can see here, there is A, B, A, C, C to D, C to E, and E and F. This is basically a DFS algorithm, but obviously if you use Networkx, like you can just call a function called DFS edge. You give a parameter your graph G as starting node point, and there is other parameter that you can add. As you can see, there is a example here that do the same. So let's just do that and see if our implementation is correct. So let's create a G graph called G nx dot graph right here, pass it a graph. So we create a graph. So let's just create a call our function. So let's say nx dot DFS edge graph G and a starting point A. So let's just print it the way it is. Okay. So let's just run it to see. As you can see, there is basically here that is the same. So that's it. Basically, that is DFS algorithm. It is a very useful algorithm used in ladder application, especially in game to exit out a maze, especially for backtracking. So that is DFS, another graph traversal algorithm. So if you like what you see, please like and subscribe. So I will make another video for the graph Networkx series. So thank you.